So in the last class, we discussed what are the various criteria that governs the liquefaction potential of a soil, and uh, how they affect whether a soil will liquefy or not, and how they will liquefy, right? Even the behavior of the soil, how they govern the behavior of the soil after the initiation of liquefaction, or when they will liquefy, how will the pore pressure develop, how will the soil behave, whether there will be a flow liquefaction or whether there will be a cyclic mobility and various other factors. So today what we are going to discuss is how we evaluate whether there will be liquefaction or not. All right, so we have to estimate, we have to get a fair amount of estimate that there is a probability of liquefaction. Okay, so there is a chance, or you can say a probability that liquefaction may occur. Now to evaluate that, what we do is, first of all, we find out what stresses. So as we have discussed earlier, so when there is an earthquake, so a particular element in the soil, so we have the sigma vertical and we have the sigma horizontal, and then when there is seismic shaking, there is shear stresses applied, so there is tau h. All right, so first of all we assess what may be the maximum shear stress that may be developed during the earthquake. All right, so that is the first step. Then in the next step, what we do, we find out what is the resistance against liquefaction of the soil. Right? So we find out, basically we find out what is, so suppose for that particular shear stress, for that particular shear stress, how many numbers of cycles. So we know that there is a relation of peak pulsating shear stress to the numbers of cycle, right? So as the peak pulsating stress decreases, the numbers of cycle increases. So we have seen that. So for that particular shear stress, what may be the number of cycles required, or if we know the number of cycles, what may be the shear stress required. All right, so ultimately we find out what is basically the resistance of the soil, cyclic resistance of the soil, which is the peak cyclic shear stresses needed to cause liquefaction in n cycles. All right, and that n cycles is same as what we assume that there may be in during the earthquake, right? So ultimately we find out that, and we plot the two. So this is the peak resistance or peak cyclic shear stress needed to cause liquefaction, this amount, and this is what is the shear stresses caused or developed during the earthquake. So when it exceeds the resistance of the soil, there is liquefaction. So we define a factor of safety against liquefaction in that manner. So what are the steps we can summarize? First of all, number one is we consider the earthquake. We first of all consider the earthquake. Alright, so we have to establish the design parameters of the earthquake. Now this is a different chapter and we will deal with it in detail in that chapter. So these are the design parameters of the earthquake. So basically for our case, that is evaluation of liquefaction potential, what we require is first of all the acceleration, maximum acceleration that may occur in that earthquake, particular earthquake, and what is the equivalent numbers of cycle. So we know in an earthquake it goes like this, right? So how many times there are reversal of stresses? So the numbers of cycles. So that is basically what is required. Now once we have that, we can get the shear stresses at various depths, right? So we can get the shear stresses at the various depths. So at this depth, what is the shear stress? At this depth, what is the shear stress? All right. So at various depths, and we can determine also the time history. So from the time history, we can get the n numbers of cycle as well as A max. All right. Then apart from that, obviously, as we have discussed, in our case, we need to know what is the peak cyclic shear stress needed to cause liquefaction in the soil. So for that, what do we need is we need the grain size distribution of the soil at various depths. So especially we need the D50, that is percentage 50% finer, or the diameter at 50% finer. So that is what we require. Then apart from that, one very important parameter that we require is of course the depth of groundwater table. Okay, so this is the depth of groundwater table. So these are some of the important parameters that we require in the analysis. So now how we do the analysis? First of all, we need to find out the shear stress, all right, or tau max as we may say. That is this one at various depths, okay, at various depths. So suppose at a particular depth h, so what we do, we assume the column of the soil on top of it to be, initially we assume that it is rigid, okay, and this entire column is moving above this plane. So there is another mass here, another mass here. So we have this plane of shearing over here, so we can consider this soil column, okay, of unit area. So this is unit area, right? Just like in direct shear now. So just like in direct shear, so suppose this mass, so first of all we need to assess what is the mass of this. So obviously area, so area into height is the volume into unit weight, is the weight of the entire column, soil column. Weight of the soil column, that is. So weight of the soil column. Now, if I divide it by G, W by G, I will get the mass M. Okay. And if I consider unit area, alright, so I will get the density, that is. Okay. So density at the depth H. Alright. So at this particular depth, we have gamma into H by G is the mass. Alright, so A is unit area, so A is unit area, so 1 unit area. Alright, so this is the mass over here, and if we know the acceleration that may occur in this column at this depth, alright, at this depth, from the design earthquake parameters, if we know the Amax that may occur, so unit weight into Amax is the force acting on this. So ultimately this is unit area, so we can consider that as tau max. Okay, so that we can consider as the tau max. So the shear stress on this plane is given by tau max is equal to bulk unit weight, alright, or unit weight of everything that is on top, into H into A max by G. Now this A max by G is a very important design earthquake parameter. Okay, so that of course we will see how we can approximate that in this particular analysis, and of course in the other chapter, that is design earthquake parameters, we will deal with this particular thing in detail. So this is the maximum shear stress. Now thing is that soil, as we know, the entire column of the soil at depth H, it will not move in this manner. It will not move as a rigid column, right? So it will bend in this manner. So as a shear wave will move up and down, it will bend in this manner. So basically this amount of shear stress will not be applied on this column, on this plane. Okay, on this plane. So to do that, we need to apply a reduction factor. Okay, we apply a reduction factor. So what we do is, so tau max, alright, so field is equal to, we say, the reduction factor, alright, RD, or it in some books it is CD, alright, so into this tau max, okay. So that is the actual shear stress which is being applied on this particular plane due to the earthquake. So Yeah, so here what we have, so this column, the soil, when there is a shear wave, so the column of soil will behave as a deformable body. All right, it will behave as a deformable body instead of what we have assumed here as a rigid body on top. So instead of this, it will be behaving like this. So we have, so instead of here tau max, we have tau max field is equal to reduction factor into the tau max. Okay, so Sedan Idris in 1971. Okay, so Sedan Idris in 1971, they gave a reduction factor based on in situ analysis, okay, or in situ data. All right. So based on in situ data, they gave a reduction curve basically. So they said that the reduction factor varied with depth. So here you see at depth 1, I mean at depth 0, sorry, at the surface it is almost 1, all right. And as we go below up to 30 meter, you can see, so there is a reduction in the shears. Basically thing is that what they say that what this means is that so we have suppose a rock formation here and at the depth of 30 meter. So from here the waves will be higher as we go up. All right, the force or the acceleration will be higher as we go up, and as we go down, the acceleration will get reduced. So the shear stresses which will be acting on the soil element at the depth will be reduced by this factor. Obviously, again we have to consider the weight of the entire soil mass on top of that element as well. All right, so that weight or that height of the soil element will increase the value of tau max, whereas the actual in situ there is a reduction factor now, so that will reduce again. So the tau field will be, so suppose at 30 meter depth it will be around this value of CD. So this is an average. We may take one average value with depth. So this is a range of different soil profile. So for different soils we have a range which they have defined. And they have also I mean as a thumb rule they have said that the depth, actually the depth of the critical depth of liquefaction actually varies in between this range. Okay, so I mean it is mostly above or just near to 12 meter and in this range, so there is maximum probability of liquefaction. So that based on that they have given the this reduction uh, factor. Again, what they have said is that the shear stress which occurs in a particular soil element, it is 65% of the, so they have, this is called the average equivalent uniform shear stress. Okay, so average equivalent uniform shear stress, so they have defined a term, so they have defined the term average equivalent uniform shear stress All right, so they have defined the term then average equivalent uniform shear stress. So why they have defined this term? Now we are analyzing as such. We are here, if you see, we are analyzing that the acceleration is only occurring on one side. So it is, I mean, we are applying a constant force. I mean, we are considering like that in the analysis. But in actual case, what will happen is that there will be reversal of stresses. All right. So what they did is they defined this term. So if we consider a constant force for the analysis, we take the average equivalent uniform shear stress as 65% of the peak cyclic shear stress, right? So in a particular earthquake, so there will be like this, and suddenly there will be a huge amount of peak, and then it will be like this. So of the peak shear stress, all right, or the maximum acceleration, whatever we have considered, so they have considered the 65% of that cyclic, that is the tau max. Okay, so they consider tau av now is equal to the reduction factor rd or ct or whatever way you use, all right, and gamma h into a max by g and 65% of this. Okay, so I mean tau av is equal to 0.65, we can say, into, so rd we have reduction factor, then gamma h we have, which is the stress at a particular depth, into a max by g. Okay, so this is the shear stress which will act at a particular depth h from the surface. All right, obviously r and rd, all right, reduction factor will also change with h. All right, rd is also a function of h. All right, so that we have to take into consideration. Obviously a max will also be actually a function of h. Okay, so there are various other factors to consider, but in analysis we mostly take a max constant with depth. All right, and the reduction factor actually, I mean, takes into account whatever reduction needs to be done in the shear stresses. All right, so we have reached the maximum shear stress that we need to take into consideration. So this part we have, so this particular curve we have now drawn. So this particular curve. Okay, now we need to arrive at different values for this. So we need to now find out the stress ratio that will cause liquefaction of the soil. All right, so here one more data that we need apart from grain size is obviously the density. All right, the density of the soil. So we need to assess the dry density of the soil. saturated density, and the void ratio. So these are some important data which is required for the analysis. So here what was done was, so this particular curve was obtained by Seed and Peacock in, was given by Seed and Peacock in 1971. So what they did was they did several tests. All right, so several tests they did. So here sigma dc, so if you see, this is sigma dc. So sigma dc is the cyclic deviatoric stress. Okay, so we apply the deviatoric stress. So the cyclic deviatoric stress, whatever was applied, so that is the sigma dc. All right, so basically sigma dc by 2 by sigma a. All right, so sigma a is basically the ambient consolidation pressure. All right, so that is the consolidation, that is the initial consolidation up to which the soil was consolidated before testing. All right, and the mean grain size, so these are the mean grain size. So once we obtain the values of the grain size, so we can obtain the stress ratio that will cause liquefaction. Right, so this is for numbers of stress cycle, 10 numbers of stress cycle. So this is NC equal to 10. Okay, and similarly for NC equal to 3 also they obtained NC equal to 30. So NC equal to 30 they have obtained. All right, so they have obtained, so this is a stress ratio. So this is the stress ratio they have obtained for various initial confinements. So sigma V dash in the field, we can see in the field. We have to find out this accurately. All right, so the effective pressure, effective stress in the soil in field, we have to very efficiently assess. All right, so that is one also important parameter in the analysis. So once that is obtained, so we can find out what is the deviatoric stress. All right, so sigma dc by 2, which will be required to cause liquefaction once the mean grain size d50 of the various soil is obtained. So we here have suppose the mean grain size d50, so we obtain the grain size distribution, and the d50 we obtain that it is 0.01. All right, 0.01 mm, that means. So we now find out, now this is for N30. Okay, N30, NC30, that means number of cycle 30. For number of cycle 10, it will be this one. So here, so we will combine this. So suppose we have here we have N30 and we have N numbers 10. So if somewhere in between we can interpolate. So what is the stress ratio? All right, so we are here, we have sigma d by 2 by sigma 3 is equal to here you may say that it is 0.22. All right, so that is the stress ratio. Then for NC30 you can say that it is point maybe 1 something. Okay, So you can see with numbers of cycle increasing, we require less amount of deviatoric stress now. Right? So here in this case it is sigma d2 d by 2 is equal to 0.22 into sigma 3, whereas in this case it will be sigma d2 will be equal d by 2 will be equal to 0.17 suppose. So 0.17 into sigma 3. So with increasing numbers of cycle we have lesser deviatoric stress required to cause liquefaction. So once we obtain that, so these are obtained, all right. So from there we can plot now this one, right? So sigma v dash will be at different depths, different. Okay, we know what is how to calculate that. So we have found out. So gamma h minus gamma w into here it will be h minus dw. All right. So that will be the sigma v dash. So once sigma v dash is obtained, so we can find out sigma d by 2 is equal to, once the ratio from here we have got, all right, we have got. Then again, so Seed and Idris in 1971 themselves, what they have given is that correlating with earthquake magnitude. So with earthquake uh, magnitude, they have correlated with the numbers of cycles. So they have correlated with the numbers of cycles. So if it is 7 magnitude earthquake, so it is approximately 10 numbers of cycle. So we will consider this one cycle. All right. So if it is 8 magnitude, so it will be approximately 30 numbers of cycle. So this is the curve to be used for the design analysis. All right. Again, in the last class, we have found out the correlation correlating to simple shear. So in simple shear, tau h by sigma v dash. All right. So we have found out that there is one correlation alpha dash to sigma deviator stress by sigma 3 in the last class that we found. So there are very different values of alpha as derived by Sedan Peacock and then Castro 1975. So based on those alpha values, you can find out what is the tau h required. All right. So you can plot the tau h here. Okay. So you plot the tau h here and you plot the tau average here. So the depth at which the tau average value, which we have obtained from this particular slide here. So this is the value of tau average, and here we have obtained sigma dc by 2. What are the different stress ratios here for different numbers of cycle? All right, so for different magnitudes we have obtained sigma dc by 2. So tau h by sigma v is equal to alpha dash into sigma d by 2 by sigma 3. All right. Then there in the last class also we saw that there are various correction factors for these values as well. All right. So we use those correction factors and then we obtain what is tau h. All right. So tau h we obtain, and then so sigma v dash will change with that. Sigma v dash will change with that. So tau h will change with that. And we plot the two curves. So tau average. So this is tau average. So I will plot the tau average different colors. So this is tau average here. All right, and this is tau h, all right, which is the peak cyclic shear stress required to cause liquefaction of the soil. So we will obtain this kind of curves. So here we will see that this is the stress causing liquefaction. So here you see it went below this part here. So this is the peak shear stress required for causing liquefaction, and here this is the maximum stress. So here this curve, it went way beyond, it went past the maximum resistance, right? So this is the zone of liquefaction. So this, from this depth to this depth, we have the zone of liquefaction. So this is in, it is given in feet. Okay, you can change it to meter or whatever way you want. All right, so units are, of course, for different units you will have different x and y axis, but ultimately in situ you will find that this is the zone of liquefaction. Okay, now using the above concept, what we can do is, so here this plot, what it shows is, so A max by G. All right, so we have the A max by G as here what we have obtained. So here, so this is the A max by G. So for different numbers of cycle, for different depth of water table, and for different values of D50. Right, so that the here you see it is 0.075 meter. All right, so that is the value of D50. That means the 50% finer in the soil. So for that we obtain a curve. So first for A max by G versus relative density. So in the field, when you get the relative density of the soil, all right, and you can develop this curve for the values which you require. Okay, for the values which you require. So here so then you find out where your, suppose in situ, in the in situ, so we have the A max. All right, so we have the A max and we have the relative density. So in situ, then we obtain where this point lies. So suppose the point, now we have this A naught point here. All right, so we have a relative density of suppose less than 40, so it is around 35 maybe. All right, and we have this A max. So this point here, so that soil, that means that soil strata is prone to liquefaction. Okay, so for similarly, what we can do is, we for different values of A max by G, for different values of A max by G and for different relative densities, and for different values of d50 and n numbers of cycle. All right, so this is for d50 0.2 mm, and then we have this curve. All right, similarly for d50 0.075 mm and n numbers of cycle 20, we have this curve. So if the point, so we have a max by g, suppose in this range. All right, so a max by g, so we have this is the design earthquake. So if the soil relative density lies in 40 mm, so here, so it is prone to landslide for this magnitude earthquake. All right, so it is 7 magnitude earthquake, and this is around 7.5 magnitude earthquake. Okay, so here what we see, so if the relative density is suppose 80, if the relative density is suppose 80, then for the design acceleration, earthquake acceleration, we see that that particular soil is not prone to liquefaction. Right, so we have a design acceleration, and just we need to find now the relative density at the field. Right, so obviously for different mean grain size and different stress ratios, the design curves are already established. So from these design curves, all right, so we can establish curves of this sort. All right, so where the main inputs are the numbers of cycle, the depth of groundwater table, and the percentage finer radius, 50% finer radius. What is the radius of the 50% finer soil? Of course, A max by G will be a design earthquake acceleration here. So suppose here we take 0.1. So 0.1, so A max is 0.1 G. All right. So if it is here, so we can just, now what we need to do is we need to find out the relative density at the site in this in situ condition. So if it is more than this range, so it is liquefiable. If it is less than this range, it is non-liquefiable. Right, if the acceleration is of this range, so we can see that it has to be higher than, the relative density has to be higher than 60%. Okay, now apart from that, what Sid, Mori and Chan in 1977, what they did is they correlated the cyclic stress ratio ratio required for causing liquefaction, right? So tau by sigma naught they have written, all right, to the n value for causing liquefaction. So if it plots so here on from here, so what we have to do is we have to find out from, so suppose for n numbers of this n value, SPT n value. So what we do, we find out the SPT n value on in the site. So this is of course a very frequently done test as far as Indian conditions or Indian procedure or Indian standard operating procedures are concerned. So SPT n value is always available in situ. So from that SPT n value, of course, it has to be corrected. So it is correlated to the stress ratio causing liquefaction in the field and the SPTN value. So suppose at a particular depth we have SPTN value 15. So SPTN value is 15. So here, what is the stress ratio that may cause liquefaction? So this is the stress ratio. So if it is below here, all right, so if it is below this range, that means if it is 0.1, there is no liquefaction. All right, so what is the stress ratio? So suppose we have this one, so SPTN value is suppose 20. So that means we need tau by sigma naught is equal to 0.2. So tau is equal to 0.2 of sigma naught. All right, so that is the what Chen, Seed, Mori and Chan they did in the using the various data available in situ. So they found out this correlation. So here once this particular acceleration ratios, the stress ratios are obtained. So once the stress ratios are obtained, so you can definitely plot where there will be liquefaction or not. So this is tau v by tau h by sigma v. So these are the stress ratios, and for different SPTN values, we can get the different values here. All right. So once the ratio is obtained, you obtain the ratio. Once the ratio is obtained, you plot it here. Once you have obtained sigma v, so you can find out what is tau h at that particular depth. So once you find out tau h at that particular depth, you know tau average, all right, and you plot it. So if tau average is more than tau h, so definitely there will be liquefaction. If tau average is less than tau h, so that means there is low chances of liquefaction. Right? So what seed 1979 what they did is they correlated with different acceleration, all right, and different numbers of cycle. So for different magnitudes of earthquake, different curves were obtained, right? So this is for a particular magnitude of earthquake, all right, and then this was interpolated to different extrapolated basically to different values of earthquake magnitudes. So now with this help, what we can do with this curves, what we can do, so we can plot. So suppose we have the soil layer. Okay, we have the soil layer. So in the soil layer, first of all, we find out what is the tau average. All right, so tau average. So tau average we can find out for different magnitudes of earthquake. So tau average is equal to 65%, 0.65% of then reduction factor into gamma h into A max by G. Alright, so for different magnitudes of earthquake, we will have different A max. So we can plot the, sorry, it will be of this pattern. So for different magnitudes of earthquake, we will have different cyclic stresses induced in the soil. So similarly, again for the different magnitudes of earthquake, we can also obtain different stress ratios which are required based on the SPTN values, right? So if you consider 6 magnitude earthquake, so for 20 SPTA value n, the stress ratio required will be SPT value 20. The stress ratio will be tau h by sigma v is equal to 0.3. So tau h is equal to 0.3 sigma v dash. Okay, now with depth we can plot the stress ratio in that manner. So we can plot the stress ratio. So we may see that for a magnitude earthquake 6 there is no liquefaction. Alright, so again for magnitude earthquake 7.5, so we will have this sort of curve. So we may see that there is some amount of liquefaction. Alright, again when the magnitude increases to 8.25, so we will see that now for n value 20, we can see it is almost only in 0.2, whereas for magnitude 6 it was 0.3. So now it will be of suppose this sort. So we can see that significant depth of the strata, it is prone to liquefaction. So in that way we can assess what will be the scenario for different magnitudes of earthquake. Okay, so this is a very simple and easy way to assess the liquefaction potential in situ. So what are the data which is required? The data which are required is first of all we need to know the grain size distribution. Grain size distribution. Alright, basically the D50. So from the D50 we will have Amax, we will have a relation of Amax by G to the numbers of cycle, and to the relative density, right, for liquefaction occurrence. Then we need to find out the density of the soil. So density means the dry density of the soil and the saturated density as well. So we also need to know the porosity, that will be helpful, right, or the void ratio. Then we need to know the depth of groundwater table, DW. Alright, so this is a very important parameter, depth of groundwater table. Then we need to know, so from this, alright, once we know the dry density and the saturated density and the bulk density and the void ratio, so the densities at different depths can be calculated. So we can assess the vertical stress very efficiently. Right, so this is one important parameter in the analysis of evaluation for liquefaction potential. All right, so then from there, then we also need to know the SPTN value. So if we know the SPTN value, we can directly find out the cyclic stress, peak cyclic stress required to cause liquefaction. So that is the peak cyclic stress ratio. So tau h by sigma v field. So we have this ratios. All right. So another thing is that here also we need see that there is the limited strain potential. Obviously, as we go on increasing the values of n value, so straining is also reducing. All right. So lower values of n, higher amount of strain, and higher n values, that means denser soil, so limited straining. Okay, but see then Idris 1979, so this is given by seed 1979. So they have told that this is not very accurate in predicting the limited strain potential, and of course the SPT I mean, method of evaluating liquefaction potential also cannot accurately predict the cyclic mobility. So though, and of course though it is conservative, all right, so it will I mean the liquefaction potential, it always gives I mean higher chances, or it shows higher chances of liquefaction than it is actually in the field. Though it is conservative, still sometimes it may miss out on whether there will be occurrence of cyclic mobility in that case or not. So apart from that, so yeah, so this is how we obtain the maximum shear stress and the uh, peak shear means stress required to cause liquefaction, and the shear stress in situ, and we compare the two, and we assess whether there will be, well, whether there may be liquefaction or not. Yeah, apart from that, Ishihara in 1985, 1985 Ishihara, so gave some limiting acceleration, all right, so for certain conditions. So if this is the groundwater table, if this is the groundwater table, and this is the sand which is prone to liquefaction, and this is H2 and this is H1. So this is H2 and this is H1. So for various values of H2 and H1, we have a limiting liquefaction, acceleration, Amax. Gal is Galileo, it is Gal is actually a unit of acceleration, so it is named after Galileo Galilei. So it is equal to 1 centimeter per second square, okay, per second square. So that is Gal. So for different thickness, so then again he said, so this is a sand, this is the sand which is which can be liquefied. So this is the thickness is H2, all right, and this is the unliquefiable soil. All right, so it is H1. So it is suppose very stiff clay. All right, so this is H1 here. So this is unliquefiable. So this should be considered as H1, and this is H2. And if the groundwater table is below here also, so the entire depth should be considered H1. All right, so this is H1 and this is H2. And from there he gives some Amax values, limiting values of Amax. So based on that, you can find out the ratio of Amax by G, and therefore there is a limiting value of tau average. All right, so that is what he told. So we see that here seed 1979, he has given curves for different magnitudes of earthquake, for different magnitudes of earthquake. So these are different magnitudes of earthquake. So 6, 7.5, 8.5. All right, and he has given different stress ratios. So based on sigma v, which is the normal vertical effective stress, all right, and the shear stress. So when we find out what is the condition, effective stress condition on the in situ field, we can find out what is the shear stress peak pulsating shear stress which will be required to cause liquefaction. Okay, so based on the SPTN values. So this is SPTN values. Again, we find out the tau average, which is very easy. So this is called the stress ratio method for finding out the liquefaction potential. Of course, there are different methods also. Instead of SPTN values, we can use the cone penetration values, right? Cone penetration values. Then there is limiting strain. All right. So this is based on stress. So this is a stress method, stress based method. Then there is a strain based method as well. So what is a strain that may cause liquefaction? So we have seen that for loose sand there is a high amount of strain. For dense sand there is a low amount of strain. So what is a strain criteria for liquefaction? So there are different criteria as well. So yeah, so this is how we evaluate the liquefaction potential. So based on the SPT values, it is not very tough. Instead, not very complicated. Thing is that the values are somewhat conservative, but then again, in certain cases of cyclic mobility, it is unable to predict the occurrence of cyclic mobility. So it may show that there is no liquefaction, but there may be occurrence of cyclic mobility. But in that case, the strain may be limited because the soil will be mostly dense, so relative density will be high. All right. Then again, we see that based on grain size distribution, all right, based on grain size distribution and the peak acceleration ratio, all right, and the relative density of the soil, also we can find out whether the soil will liquefy or not. All right. So this is the different various methods of how we evaluate the liquefaction. So ultimately, what we do is we draw this. One is the peak stress required for causing liquefaction, right? One is peak stress required for causing liquefaction, and the other is the maximum shear uh, stress which may occur during an earthquake. So this is tau AV and this is tau H. So after we plot, when tau H is less than tau AV exceeds, so we have the zone of liquefaction. So for different, as we saw here, for different earthquakes, we will have different values of cyclic stresses as well as definitely different values of the shear stresses induced due to the acceleration in the soil. So definitely magnitude, for a magnitude 6, Amax will be way less than for the magnitude of 8.25 or 8.5. So in the earthquake design parameters, based on earthquake for the analysis of design parameters, in that chapter we are going to discuss how we can evaluate, how we can find out what is the various ranges of acceleration Amax